Welcome to Operations Research. Today, we are going to explore one of the most fascinating and powerful ideas in linear programming, known as the concept of duality. Imagine looking at a single complex transaction from two completely opposite perspectives. That is exactly what we will be doing mathematically today. Let us dive in and build your understanding from the ground up. To understand duality, imagine you are buying ingredients to bake a cake. You want to spend as little money as possible to get exactly what you need. But now, imagine the shopkeeper selling to you. The shopkeeper wants to make as much money as possible from your purchase. You are both looking at the exact same transaction, but from completely opposite viewpoints. In operations research, every mathematical problem we create has a hidden mirror image attached to it. If the original problem is about maximizing profit, its mirror image is about minimizing cost. Understanding this mirror image often gives us a brilliant shortcut to finding the best possible solution. Now that we understand the basic idea of looking from opposite sides, let us give these sides their proper mathematical names. In linear programming, the original problem we formulate is called the primal problem. The word primal simply means the first or original version. Its mirror image is called the dual problem. The concept of duality states that every primal problem has a corresponding dual problem, and solving either one gives us the exact same optimal value. This is incredibly useful because sometimes the original problem is highly complex with hundreds of rules, while its mirror image is much simpler to solve, saving massive computational effort. So, how do we actually find this mirror image? We must follow a strict set of rules to convert the primal into the dual. First, if the primal is a maximizing problem, the dual will always be a minimizing problem. Second, the coefficients in the primal's objective function become the right-hand side limits of the dual's constraints. Similarly, the right-hand side limits of the primal's constraints become the coefficients in the dual's objective function. Finally, the rows of the primal's constraint matrix become the columns of the dual's constraint matrix. It is a perfect structural flip. Let us look at the mathematical representation of a standard primal objective function first. Here, ZP represents the total profit or value we want to maximize in the primal problem. The symbols C1 and C2 are the profit contributions of each activity, while X1 and X2 are the decision variables, representing how much of each activity we actually do. As we increase the values of X1 or X2, the total profit ZP increases. However, we cannot increase them forever. This objective is subject to resource constraints, which limit how much we can produce based on the materials available to us. Following our conversion rules, we can now write the objective function for the corresponding dual problem. In this dual formula, ZD represents the total cost we want to minimize. Notice that the B1 and B2 values, which were the resource limits in the primal constraints, are now the coefficients here. The new variables y1 and y2 are the dual variables. These represent the hidden value or shadow price of each resource. As we use more resources, the total cost we are trying to minimize is affected. The constraints for this dual problem will ensure that the assigned value of resources is at least equal to the profit they bring in. Before we move on to more theory, let us see this conversion with a concrete example. Suppose a carpenter makes tables and chairs to maximize profit. We want to maximize the profit function Z equals 3x1 plus 5x2. This means $3 profit per table and $5 per chair. We are subject to two constraints. The first is wood, 1 unit for a table, 2 for a chair, with a maximum of 10 units available. The second is labor, 3 hours for a table, 1 for a chair, with a maximum of 15 hours available. This is our complete primal setup. Now, let us convert this primal problem into its dual. Since the primal maximizes profit, the dual minimizes resource valuation, which we will call W. The resource limits, 10 and 15, become our new objective coefficients, giving W equals 10y1 plus 15y2. Next, we convert the columns of the primal into the rows of the dual. The coefficients for tables become the first constraint, ensuring the resource value is at least the $3 profit. The coefficients for chairs become the second constraint, set against the $5 profit. We have successfully formulated the dual problem, and it can now be solved independently. The final answer shows our complete dual model. Now that we have successfully converted our problem, let us look at the fundamental theorems connecting their answers. The first is called weak duality. Weak duality states that for any valid solution you find for a maximizing primal and any valid solution you find for a minimizing dual, the dual's total cost will always be greater than or equal to the primal's total profit. In simple terms, the cost in the mirror problem acts as a ceiling or a roof over the profit in the original problem. You can never make more profit than that ceiling. Let us write this relationship mathematically. The formula is simply Z sub P is less than or equal to Z sub D. In this inequality, Z sub P is the objective value of any feasible solution to the primal, and Z sub D is the objective value of any feasible solution to the dual. This means if you pick random valid numbers for both problems, the dual answer will always sit above or equal to the primal answer. It acts as an upper bound. If the primal profit increases, it will eventually hit this dual cost ceiling, but it can never break through it. This brings us to the second theorem, strong duality, which looks at the very end of the optimization process. While weak duality applies to any random valid solutions, strong duality says that when you find the absolute best optimal solution for both problems, their final values will be exactly equal. Strong duality guarantees that at the finish line, the buyer's lowest cost exactly matches the seller's highest profit. If the primal problem has a valid optimal solution, the dual problem is guaranteed to have one too, and their final numbers will match perfectly. Mathematically, strong duality is expressed as ZP star equals ZD star. Here, the star symbol indicates that we are looking at the optimal, absolute best solution. ZP star is the maximum possible profit and ZD star is the minimum possible cost. When you reach the peak of the primal problem, you are simultaneously at the lowest point of the dual problem. If one variable increases to its absolute limit, the other decreases to meet it perfectly. This equation is the heart of duality, proving that both paths lead to the exact same destination. Let us verify this incredible concept of strong duality using a very simple, intuitive example. Imagine a primal problem where we want to maximize profit based on a single product. We make $4 for every unit, so we maximize Z equals 4x1. However, we are limited by a single constraint. We cannot produce more than 5 units, so x1 is less than or equal to 5. It is obvious that to get maximum profit, we should make as many units as possible. So we set x1 to its maximum limit of 5. Calculating this, our optimal primal profit is $20. Now let us construct and solve the dual of this exact same problem. The objective is to minimize W equals 5y1, using the primal's limit of 5 as our coefficient. The constraint uses the primal's profit, so y1 must be greater than or equal to 4. To minimize W, we should pick the smallest allowed value for y1, which is exactly 4. Let us calculate the optimal dual cost. We get 5 times 4, which is also $20. As we can see, both the primal and the dual give the exact same final answer of 20. This perfectly demonstrates the theorem of strong duality in action. So we have proven that these optimal values match perfectly. This brings us to an important question. Why do we go through the trouble of creating this mirror image? In the real world, businesses often face problems with thousands of constraints, but only a few variables. Solving such massive problems directly takes a lot of computer power. By converting to the dual, thousands of constraints become thousands of variables, and the few variables become a few constraints, which computers solve much faster. Furthermore, the dual variables represent the shadow price, telling a company the maximum amount of money they should be willing to pay to get one more unit of a resource. Let us look at a visual summary of everything we have discussed. On the left, you see the primal problem box, which seeks to maximize profit subject to resource limits shown below it. On the right, you see the dual problem box, which seeks to minimize cost subject to profit requirements. The large double-headed arrow in the center represents strong duality, the powerful theorem guaranteeing that despite their opposite approaches, both problems converge on the exact same optimal value. This diagram perfectly captures the beautiful symmetry of linear programming. To wrap up our lecture, let us review the key takeaways. Duality is the concept that every linear programming problem has a corresponding mirror image. If the primal maximizes profit, the dual minimizes resource costs. We convert them by flipping the objective, swapping coefficients with limits, and transposing the matrix. Most importantly, strong duality guarantees that solving either problem gives you the exact same optimal value, providing deep economic insights. You have now mastered the fundamental concept of duality. Excellent work!